Hello everyone, my full name is Ngọc Duy with the student ID S224916123. Today I will demonstrate my solution for task A1, wraps, path, and Miss Marple. In part A, we will work with the unweighted wrap. This means that in that wrap, each of H have 1 unit. The goal in this part is that we will have the Miss Marple to find which is the hotel, not V, have the maximum number of shortest path from the train station, not S. So to resolve this problem, because we are dealing with the unweighted wrap, so I use the breadth first search starting from the north S to find how many shortest path of each node from the train station. So we're gonna use two arrays. The first one is shortest path. So in the shortest path is we store the number of shortest path from each node to the train station, and the distance store the distance between each node to the train station. So the algorithm work at the beginning, because all of the nodes are not visited, so the shortest path of each node equal to 0, because we currently we don't know how many shortest path of each node at the beginning, and the distance from the node to the train station is -1. So I put the -1 here. It means that they are not visited yet. So next, we will put the node S into the key and start the PFS search. So initially we will set the node S, the shortest path of the train station to itself is 1, and the distance of the shortest path to itself is 0. Alright, so while we're working with the PFF search, we're gonna meet two scenarios. So the first scenario is that we visit a neighbor, and this neighbor is the first time we visit it. So there are two things we have to do. So the first one, that we have to update the distance of this neighbor. So the distance of a neighbor is equal to the distance of the current node plus 1. We plus 1 because we're working with unweighted wrap, and in the unweighted wrap, the number of each edge have 1 unit. And the second thing that we have to do, we have to update the shortest path from the neighbor to the train station. So it's equal to the shortest path of the current node. So why? So let me show you an example. So here we have like the station S and two nodes A, B, and C, and the node D, and the route maybe like that, for example. Yeah, so you can easily notice that from S to C we have two shortest path. So SAC and SBC, and because that and D is a neighbor of C, so because this is the first time we visit D, so there is only exist one path from C to D. And the question is how many the shortest path from S to D? It's 2, because if S want to go, if from S we want to go to D, we have to go through C, and there's 2 shortest path to go to C, so we also have 2 shortest path to go to D as well. I hope this makes sense. So that is the first scenario. The second scenario is that we visit a node, but this node was visited before. It means that there already exists a shortest path from S to D before, and we have found a new road. So the new road doesn't mean that it's also the shortest path, so we have to check. So this is the condition to check if the new row is also the shortest path as well. So let me explain the condition. So here we have the shortest path S, and for example we have 8 C, and we have the node B. All right, so for example we have 8, and 8 is visit the node C already, so it means that the distance from S to C is already 2. And when B is trying to visit the neighbor C, it have noticed that D is not minus 1, so the distance of C is not minus 1. It means that C have visited before, so it have to check if the distance of C is that D2 DC is that equal to DB plus 1. It means that does can we access the not C via not B with one distance. So and it's noticed that it's equal to 1 plus 1 equal to 2. So 2 equal to 2. So it means that from SBC the road is also the shortest path because it's the distance is equal to the all path. And if the condition was satisfied, we gonna update the shortest path. We plus the shortest path by 1. It means that we find a new shortest path. Then in the next step, let me show you how the code look like. So we're gonna have the input graph as the map of the city, and the station location of the location of the train station S, and the output we're gonna output the node V, or we call the hotel that have the maximum shortest path from the station. So we have the function solve shortest path. First we create a empty key to store the nodes or the hotel of the wrap key. So the first element of the keys is the train station, because we start from the train station. Distance and shortest path equal we create a two array as I said before, the distance and shortest path. And then because at the beginning we assign each of the distance and shortest path of each node the distance minus 1 and the shortest path is 0. And because we start at the train station, so the distance from the station to itself is 0, and the shortest path, there exists only one shortest path from the station to itself, minus is 1. Alright, so that is the main part of the function here. Okay, so while the key is not empty, we dekey to get the node, and then we access each of the node n, and then we access each of neighbor u of node n. So if the neighbor u is minus 1, is that is not visited before, we do as I said, we update the distance and the shortest path, and then we put the neighbor u into the key as well. However, if the neighbor u it has visited before, so we have to check the condition. So if the condition is true, we add one more shortest path. We add one more shortest path for the neighbor u. So after the key is empty, it means that we access with all of the nodes into the wrap tree. Then we go to the next part. So this part is we access each of the nodes into the wrap tree again, and then find which node have the maximum number of shortest path from the station, and then we return that node. So that is overall the how we can solve this task. Alright, so in the next part is a time complexities analysis for this solution. So at first, because we use distance and shortest path to store the distance and the shortest path for all of the nodes into the graph. So because we have n nodes, so the number of operation, the time complexity here is on. And secondly, we use the key tree. We have the D key, and each of, because we have n nodes, and each of the node will increase into the key queue at most one time. So that means that if we increase all of the nodes, the time complexity is on as well. And then because each of h in the graph tree is connect a pair of a pair of nodes, so it means that we have a h here and it connects a and b. So when we access a and or b, we will go through the h, this h two times. So because we have mh, so the time complexity is O to m. It is also equal to om because we don't worry about a constant number. So it means that the total time complexity for the algorithm is on plus on is equal to on plus m is here. Alright, so let's move to part B. So in the part B, we will work with the network connection. The goal of the part B is that given a so let's imagine that each of computers in the network is a node, and the connection between computers are h. So uh, the the goal is to that given a node s, so we have to check that from the star node s is that exists at least one path from s to every node or computers in the network. If there is, so we can say that the network is connected. Otherwise, the node is unconnected. So the idea is very simple. So for all of the nodes into the graph, we assign them with the value called visited. So in initially, because we have not checked the connection, so we set them with 0. So 0 means that unconnected now. So then we use the BFF search to access each of the node or computers in the network, and for each of node or computers that we access, we change the visited value of them from 0 to 1. This means that from unconnected to connected. Then after the BFF search is done, it means that we have reached all of accessible computers. Then we check the visited of all nodes again, and if there is an element that it have the value of visited as 0, it means that they is not connected. Then we say that the network is unconnected. Or if all of the nodes or computers have the visited value is 1, so we say that the network is connected. Alright, so let's go to the code to see how the program look like. It's very similar to the program in part A. So let me quickly explain to you. So in the input is also the graph tree, and then the star node, the node that we start the PFF search, and the output is the pooling value true or false. So true means the computers in the network is connected, and false is that there is exist at least one computers in the network, they are unconnected. So the function called check connection is give the two arguments, the graph and the star node. We create a visited array with it have the ends with the n space. N is the number of nodes into the graph tree, yeah? And we have to create a key called q, and then because as I say initially visited index of on node is 0, means that they are unconnected now. And because we start from the star node computer, so we set the visited of the star node as 1, and we put it into the key to start the PFF search. Then it is also the main part. So we start the PFF search from the star node. We dekey the node, and then we access the neighbors of that node. So for each of its neighbor, if it's unconnected now, we change into connected and put it into the key using in queue function. And then when the BFF search, it access all of the element into the graph, we will use another part here, mean that we access each of value into the visited array. And if in the visited array there is at least one elements that have value 0, it means that there exists one computers that are that is unconnected, we return false. It means that unconnected network. Otherwise, if all of elements into the visited array have elements have the value 1, we return true. It means that we all of the computers are connected. Then the time complexities of this algorithm is O n plus m. So why? Because here at first we also assign each of value in the visited array with the value 0. So it means that because physicists have n elements, so we need we have the O n time complexity here. And also it's similar with the part 8, we have the in key here, and for each of elements, each of nodes in the graph, they are in key they are in key as mod 1. So this is also the O(n) time complexity. And also because each edge is connect to pair, each edge is connect a pair. It means that 2 nodes. So when we access A or P, we use this edge 2 times. So it means that the time complexity is O2n, and it's equal to O(n) because we don't worry about a constant number. And then we plus all of them together and receive the result is O(n) plus m. Yeah. And then let's start with part C. So in part C, we will identify the differences if we use the adjacent array instead of adjacent lists. So because we use the adjacent array, so we store the node like that. So here we have like the array here. Then we have 1, 2, 3, go on to n. So n is the number of nodes into the graph. See, we also have, so here is the column and the rows 1, 2, 3, 4. Yeah, and also go on to n. So the question is, what happens if we want to access a specific node into the graph? For example, I want to access each node, that one. So for adjacent arrays, we have to work with row and the column as well. So here we have to have a for loop to access each element into the row like that. Let's go through here. And then we have another for loop to access each element into the column, like go down here, and then until they meet we access this node. So which means that we have all end for the first loop, for example the to access each element into in the row, and then we also have another O n time complexity to access the element into the column to get the node. So it means that the total time complexity is O n squared. Alright, so in part D we will work with a directed graph G. Is presented in as a matrix A. So each of element A ij it means that the element at the row I and the column j in the matrix A means that it is the distance between the node I and the node j in the graph. So for example we have here the first one is 4, so 8 1 2 equal to 4. So it means that the distance between the node 1 to node 2 is 4. Because we're working with the directed map, directed graph, so we should we should put the arrow here to represent the direction. This means that from 1 go to 2 it's got 4 units. And for example we have 8 1 1 2 3 4 5 6 6 is equal to 10. It means that from 1 to 6, from node 1 to node 6 we have to spend 10 codes, and then repetitively for all of the element in node A we're gonna have the complete graph G like that. So that is the graph G. Yep. Yes, so after we complete drawing the graph G, so the problem that we have to do here is we have to solve the single shortest path using the Dijkstra algorithm. I'm so sorry if I read the name of algorithm incorrectly. So to use this algorithm is it means that we always prioritize the unvisited nodes that have the smallest distance, and in case if we visit a node again we have to compute the new distance, and then we compare the new distance with the old distance. If the new distance is smaller we update the distance of the node, otherwise we keep the distance unchangeable. So here let's start with because the starting node is node 1, so that the distance from node 1 to itself is 0, and node 1 is have 2 neighbors, node 2 and node 6. Then we have to compute the distance from node 1 to node 2 and node 6, that is 4 and 10. So we put node 2 and node 6 into the key, and this is the priority key, so it's always prioritize the node that have the smallest distances. So here it will prioritize 2, because 2 only have the distance is only 4 compared to 10 as in node 6. So we will remove the node 2 first, and node 2 it have 1 2 3 4 neighbors, so we have to compute the distance of all 4 neighbors using node 2. So the distance is presented over here, and then we add all of them into the key, and it's on, and the key continue to prioritize the smallest knot that have the knot that have smallest distance. So in this case, that is knot 4, the distance is 9. So then we remove the knot 4. Then knot 4, the distance of knot 4 currently is 9, and knot 4 have 3 neighbors. Then they are knot 3, 6 and 1, and then we compute the distance of them. So 11 as well, and then 15. But you can notice that we have visited knot 6 and knot 1 before. Knot 1 is the starting knot would have the distance is 0. So because the distance here is 15, so we don't update the new distance of knot 1. And also the knot 6 it have the new distance is 11, but we have computed the knot 6 before, and the distance is only 10. So we also don't update the new distance for knot 6 as well. So the knot only remain is knot 3. Then we add knot 3 into the key. Then the smallest knot, the knot that have the smallest distance now is knot 6. So knot 6 is have one neighbor is knot 4, and the distance is 13. But we also visited knot 4 before. So the old distance is 9. The new one that we have just computed is 13. So it's greater than 9. So we don't have to update the new distance for knot 4. So we keep knot 4 is 9. And then the key remain the same. So knot 3 is now is the knot that has smallest distance, 11. So the neighbor of knot the neighbors of knot 3 is 5, and then we calculate the distance of knot 5 is 20. And we also visited knot 5 before, and the old distance is 15. So 20 is greater than 15, so we don't have to worry about it. We don't have to update the new distance. We keep 15. And then the keys only remain 3 knot here. Then knot 7 have the smallest distance, so we decay it. So it have 12, and then this have 2 neighbor, 2 and 6. So because we have both visited knot 2 and knot 6 before, and the old distance is both of the old distance, they are smaller than the new one, so we don't update the distance of the new distance into the key. So the key keep the same. So we only have 2 knot here. So the knot. So knot 8 is the knot that has smaller distance here, 14. So the neighbors of knot 8 is 3, so it's 24. So because the old distance of knot 3 is only 11, so 24 is very greater than 11, so we don't update the new distance. So the keys remain knot 5. So the knot 5 is have 2 neighbor, knot 8 and knot 10. So then we can compute the distance of knot 8 and knot 10, that is 15 and 18. And because we have visited knot 8 before, so the old distance is 14, the new one is 15, so it's greater, so we don't have to update the distance of knot 8. But knot 10 is an unvisited knot, so we have to add it into the key. So finally we remove knot 10. So knot 10 have the distance 18, and F have 1 neighbor, knot 4, 22. But the old distance of knot 4 is only 9, so we don't update the new distance. And then when the keys is empty, it means that our program is done. And then we have found the shortest path from the start node. So the order of removal is the shortest path from node 1 to every node. So from node 1, the shortest path is go to node 2, 4, 6, 3, 7, 8, 5, and 10. Some of you may notice that we don't have node 9. So what happened with it? So let's we move to here. As we can see, where is the node 9? So here is the node 9. The problem that we don't have the node 9 because we have the path from node 9 to node 8, but we don't have any path from another node to node 9. It means that we don't have any path from node 1 to node 9. That's why it's not included in the order of removal. And here is the shortest path tree, as you can see here. Alright, so let's move to part E. So in the part E, we are given a weighted graph, and the question is that in the weighted graph, we have the shortest path B from the node S to the node T. And the question is if we increase each of H in the weighted graph by 1 unit. So the question is this the shortest path change into another path or something? So my answer is no. The shortest path stay the same. So why? So for example, in the graph G, we have the shortest path is P1. It is so the total weight of this shortest path is W1. And for example, we have another shortest path. Sorry, we have another path, not shortest, yeah. Like P2 is associated with W2, and because P1 is the shortest path, so the weight of P1 is the smallest in graph G. So it means that in every case, W1 is always smaller than W2. And if average age of the graph G increased by 1, it means that W1 and W2, it was added the same amount. So here, so you can see that if they are added the same amount, W1 is made plus n, and the W2 is plus n as well. So what happened here? So at the beginning, W1 smaller than W2. So if they are added the same amount, so W1 is also smaller than W2. And because it is smaller, so the shortest path stay the same, is P1. It's unchangeable. Alright, so let's move to the final part F. So in part F, we have to solve the problem. So the question is that we are given a graph G, and we know that in graph G we have the negative cycle. So negative cycle is the cycle that have the negative weights. So, and we also have this C. So C is the like a list of nodes that is included in the negative cycle. And the star node S is the node that we start, and the T that the T is the destination. So the question is there exists a path from S to T that have the negative weight, so the weights less than 0. So the question is, so to check if there is a path from S to T have the negative weight, we have to let S go to the negative cycle. So inside the negative cycle, the we can go through the cycle so many times until the weights become negative enough, and then we go out the cycles and then we go to t. So we have two things to check. First, we have to check that is there exists a path from S to the cycle, and the second, we have to check if there exists a from a cycle from any node from the cycle to a destination T. Okay, so here is the code for this program. So first one is the helper function. So helper function PFS is implemented as part P. So it also have a physicist. It tell two arguments. G is the wrap and star node is the node that we start the search. So we start at the star node, and then we check if from the star node we can access any elements into the wrap G. And so visited equal to 0 is mean that not visited, and visited equal to 1 mean that it can be visited. So we use the PFS to check if there exists a path from S to the cycle or from the cycle to the destination T or not. The main function is solve. So solve is have 4 arguments: the wrap G, the list of node in the cycle, the star node, and the destination node T. So first, we have to create the array called visited 1 and put it as a result of the function breadth-first search. So here we use this one to check if there is a path from S to C. We create a Boolean value called can read the cycle. Initially we put it as false. Alright, so in each node in the cycle C, if it can be visited, mean that equal to 1. So we change the can reach the cycle equal to true. If we access all of the elements in the list C and none of them can be visited from the star node, so the can read the cycle equal to false, then we stop the program and we return false to the user. So if it's true, we continue the next part. So in the next part, we have to check if there is any path from the cycle to the destination T. So here you can see the reverse wrap function. So what is the reverse wrap? So reverse wrap will create a sub wrap that have the reverse direction compared to the original wrap. So for example, in the original wrap, we have the node 8. It have the direction from A to for example B. But after we reverse the wrap, the direction will be reversed. So it means that we have direction from B to A. Okay, so but why I have to create the sub wrap? The reason is that because we have many nodes into we're not sure that we have how many nodes into the cycle, and the time come when we want to check if there is any path from a node from the cycle to the destination T. We have to do a breadth first search for each of node in the cycle. So it is very time consuming and the time complexity is very high. So my solution here is that rather than we check is there any node from the cycle to the destination T, the more effective way we can do is that we check is there any path from the T to at least one node in the cycle. That is my idea. So that's why. So we only have to perform the breadth-first search for the node T only. So here, so if we can say that we have the path from T to the cycle, we can also say that there is also a path from cycle to the T. So after we create the reverse wrap, we can put the boolean value can reach the destination equal to false, and when we do the breadth-first search on the destination T, and for each node in T, if there is at least one node in C can be visited by the destination T, so we change the can reach the cycle equal to true. Otherwise, if there is none of node in C can be visited via T, it remain false, and then we return false to the user. So if on can reachable the cycle and can reach the destination, that's one should be can reach the destination, not the cycle. That's my fault. Yeah, so if both can reach the cycle and can reach the destination is true, we return true to the user. So what is the time complexity of this? So for the breadth-first search, as we discussed in part A and part B, the time complexity is OM plus N. And in the reverse wrap, because we have to create a new list for the subwrap, and we have the total nodes we have the ends, so the time complexity is ON. And we also have to evaluate each edge to reverse the direction, and we have MH, so the time complexity is OM, and the total is OM plus N. So the total complexity for the function solved is also OM plus N.